Well, we're here with Jim Gray, SQL God, architect, just kind enough to talk with us, programmer, extraordinaire, researcher. And, so tell us a little bit about yourself.
I work at Microsoft. I've been at Microsoft about 10 years. I'm in the research division. I'm an old guy. I've been doing stuff in computing for a long time. I love computers. I love technology. And I came to Microsoft to make supercomputers out of scalable components, which is to say, make the biggest computer that you could possibly imagine by just using the stuff that you could buy at Radio Shack.
Wow.
And you know, I mean, at the time, 10 years ago when I came, this may have seemed like a radical idea. It's not actually, it wasn't very radical then, it's not really very radical now. All computers use the same kind of DRAM. They all use more or less the same kind of disks. They all use the same kind of processors now. I mean, there was a time when people had special purpose processors. They're now all microprocessors. And in fact, what's happening is we're putting several processors on a chip. So everybody, you know, the biggest mainframes to the lowest end machine are more or less all the same stuff. It's just a question how you glue it together, and that glue is software. And so the challenge is to take thousands or millions of computers and wire them together so that they deliver some fraction of their capacity. Because if you can deliver, say, 25% of the performance of each of those machines, you're going to beat the pants off of anybody who tries to make a mainframe that is just one great big hunking machine that is incredibly well engineered, but fundamentally is trying to pour a vast amount of data through a very, very small space, because these guys have, you know, tens of thousands of disks and tens of thousands of processors, and they're just going to beat sort of the Chinese army approach, any supercomputer that you can imagine. And, you know, again, 10 years ago this was at least speculative. Now, if you look at the list, like the top 500 for supercomputing, half of them are clusters, half of them are these, you know, commodity machines. And if you look at the TPC benchmarks, which are commercial things, the highest numbers all come from arrays of processors and disks. And if you look at the way MSN or AOL or Google or Info2me or any of these, you know, very high-end services, they're all just oceans of machines that have been wired together. So it's happened, and everybody who has those systems, I mean, if you look at the MSN website, for example, it's a nightmare to manage that website. No knock on Windows, no knock on Microsoft. It's just that we haven't kept up with the demand. The design, if you're a researcher, has to be for millions, because that's where we're headed. I mean, the unit price of computers is heading to zero, and people have $1 million budgets, and so, you know, if the price of the computer is zero and you got $1 million budget, you can buy an infinite number of machines. But if they're $1 each, then you can buy 1 million of them. If they're $1,000 each, which is kind of what the unit price is, then somebody who had 1 million machines would have a $1 trillion budget.
And we're just about to
we're
just about to enter into the multi-core world. You know, even on
we already are.
desktop.
I mean,
yeah, but most people don't own one on their desk yet.
Well, actually, you'd be surprised. Hyper-threading has been around for quite a while. I mean, many of the desktops that people are buying now, most of the Xeons are hyper-threaded, and they're not as multi-core as, I mean, the AMD guys decided with the Opteron they would just go to multi-core straight out. Intel took this intermediate step of hyper-threading and then going to multi-core. But we've been dealing with hyper-threading for, I think, 2 years, 3 years. And certainly, I mean, I assume that many of the Channel 9 viewers are pretty high-end users, and so I'm guessing that most of them have a workstation that in fact is hyper-threaded, or potentially it's an Opteron multi-core.
Now, when we talk about this distributed model, as operating systems need to evolve, we need to is this gonna impact the evolution of operating systems? You need to be more network aware. I mean, operating systems today, are they optimized to play in this world? Is my question.
Oh, no.
Okay.
And first, what the operating system does, basically it's trying to virtualize resources. And the operating systems guys, for years and years, have given us virtual memory and virtual processes and files, which are virtual disks, and they're doing a great job at that. And the networking stuff has gotten amazingly better. They've given us sockets, which are virtual connections, and so they've really been in this virtualization world. But they haven't really stepped up to the fact that they have to operate a cluster. I mean, it's been sort of, they've had a pretty clear focus on what they do. And, in fairness, the database guys take a pretty clear and narrow view of what their job is. Oh, we manage data, we do SQL, we do, and they don't worry about, say, spatial data or temporal data or image processing or text search or, well, we don't do that. That's not databases. What do you mean it's not databases? Well, it's not what we do, so therefore it's not databases. Okay, so the operating systems guys, if you go and get an operating systems textbook, it doesn't talk very much about managing 10,000 machines. Okay, and the thing that manages 10,000 machines, that's not an operating system. That's something else. That's systems management, or that's, it's a network, and well, so who manages the network? Well, that's network management. Well, who does that? Well, not me.
Yeah.
So, and the problem is that basically the OS community hasn't really stepped up to this and embraced it and said this is part of our task, and it's kind of fallen between the cracks, in fairness. So. What operating systems do? I mean, clearly, in this new world, a computer is your transistor. That's what you start with. That's your building block. And you now are architecting systems where your module is a computer. I call these things cyber bricks, and you're just sort of like building this wall out of these bricks, and you're just sort of stacking them up. So what's the architecture of the building that you build out of cyber bricks? Well, candidly, this is not a very well thought out thing. Beowulf clusters were an early start. Very simple idea of, well, let's just put together a software package that includes MPI, message processing interface or message programming interface, and a file system that does remoting and a little bit of a security story and something that will install and broadcast the programs to all these guys and remote boot. And so Beowulf was in part a cookbook on how to go out and buy 100 machines and wire them together with Ethernet and so on, and then a disk, in essence, that had a software package that you could install and you could run some sample programs on, and then you were on your own. And in the science world, scientific computing world, it's been sort of the cornerstone on which most parallel systems are built. People now have gone forward and added things on top of that. Most Beowulf clusters these days are built out of Linux. There is a Beowulf Windows book. In fairness, I think we have to admit that Microsoft has been behind the curve on getting Windows Beowulf working. I think we have natural advantages there, but we really haven't focused on the group of people who are doing technical scientific computing until recently. There is now a group in the development organization that's focused specifically on addressing the needs of that community. But to answer your question one more time, there's nothing really wrong with the way operating systems are structured and work today from the point of view of this discussion, which is to say their goal is to virtualize devices. The services and facilities they provide are just great. It's that there's another layer of abstraction above the operating system, which you could think of if you were not an operating systems person, you say, oh, that's just an operating system. But the operating systems guys might say, no, that's not what we really do. But it's a distributed file system, a distributed execution system, the ability to create processes anywhere in the network. Sometimes it's called grid computing these days. Sometimes it's called cluster computing. There are certainly people who think of themselves as operating systems people who are working on this problem, but one of the reasons the problem has not made it, we haven't made as rapid progress on it as we should, is that it really is different from the day-to-day concerns of the OS guys.
You did the Terra server, right?
Well, I helped.
Okay. It's
As,
nice to see you not taking all the credit.
yeah, but no, I mean, the story of my life is that I've worked on a lot of projects, and I'm a researcher. So when I work on something, I talk about it, I write about it, and so on. So, as with the Terra server, almost all the projects I worked on, a lot of other people did most of the work. I did a little of the work. I went out and gave a bunch of talks about it. I wrote papers about it. I got credit for all the work. Okay, so the simple fact is, I didn't do 10% of the work for the Terra server. I mean, I was there at the beginning. The story of the Terra server is an interesting one. First, what the Terra server is it's terraserver.microsoft.com or terraservice.net. We wanted to have, we have a group called Scalable Computing here at Microsoft. We wanted to show off the scalability of Windows. This was back when dinosaurs roamed the earth. This was back in 1996, 1997. And we said, geez, we work on scalable servers. We ought to do something that's scalable. What does that mean? Well, a terabyte's a lot. Let's do a terabyte. Okay. SQL Server 7.5 was coming out. The SQL Server guys wanted to show off the fact that they could manage a terabyte. So they actually came to us and said, help. And we said, okay, we're game. And about the same time, Microsoft had a thing called Scalability Day that was coming out. And Scalability Day was going to, we're going to strut our scalability of Exchange, and NT 4.5 was, coming out, and new SQL was coming out, and we were running on the alpha, and the 64-bit addressing of the alpha was, was there. So we're going to show off all this great technology. And so we said, okay, well, so we need a couple of things to make this work. We need a terabyte of information. Where are you going to find that? And we had the internet, but we started shopping around, and we were looking for a terabyte that was free, because if you paid $1 a megabyte, it would be $1 million, and that was over our budget. It had to be interesting, because we wanted to put it on the internet and show it off, so it had to be interesting to everybody everywhere. And it couldn't be offensive to anybody anywhere. Okay, so I mean, interesting to everybody everywhere. Porn comes to mind, right? But offensive now, and so I mean, offensive sort of rules out almost everything. Almost everything you can think of will offend someone. Okay, so I mean, you very quickly come to the conclusion it's impossible to find a free, interesting, inoffensive terabyte. But we had been working with the earth science community on instrumenting ecosystems, and they put us in contact with the U.S. Geologic Survey that has a 1 meter resolution image of the United States. They fly over the United States and take a picture from an airplane, and they take this stuff and digitize it. And it was on their website, and if you knew the magic numbers for your digital orthoquad, you could FTP this thing from their website. And then the thing would show up, and it was in GeoTIFF, and if you had the right kind of viewer, then you could view this thing. So the data was more or less there, not all of it, but the popular parts of it. So we called them up and we said, can we have a copy of your data? And they said, how much do you want? And we said, we'd like to have all of it. So we signed a cooperative research and a development agreement, and we got all their data. And the deal was, we took their data and we mosaicked it together and gave it back to them. And that turned out to be a very useful service for them. And they'd actually never seen all the data and been able to, mouse around on it. And so anyway, we took the data and we ported it into SQL Server, and we put it up as a website. And there were other parts of that was interesting. We called up our good friends at Compaq and we said, we'd like to get a system with a terabyte of disk. And they said, first thing they said is, do you know how much a terabyte is? Because, I mean, this was the day of 9 gigabyte disk drives. So, in those days, a terabyte was a lot of disk drives. And, of course, they had to be mirrored in those days because disks were less, and so on. So it was, a lot of disk drives. And, in fact, they couldn't attach that many disks to one compact system at that point. Dual processor Intels were the high-end quads were rumored. The machines were a lot smaller. 100 megahertz was the norm speed. So we went back and forth, and it concluded eventually that we needed to work with alphas. And so we talked to Digital and originally deployed on an alpha with, in round numbers, about 250 disk drives. And it was a machine that it was the largest PC in the world at the time, I believe. It was 6 cabinets long.
Wow.
And the embarrassing thing is, at the time, it wasn't actually a terabyte. It was a little bit short. It was a decimal terabyte, not a binary terabyte. And as huge as that machine was, we actually had only 600 gigabytes of data in it when we went live, because that's all we could get from the USGS. And it was a while before we actually ramped up to the terabyte. The Terra server now is up at 6 terabytes of storage, and has the topo maps for the U.S., photo maps of the U.S. For many cities, about 50 of them. We have 1-foot full-color resolution imagery, all courtesy of the U.S. Geologic Survey. Very, very nice website. So I was involved with the Terra server, but the guy who deserves 99% of the credit for it is Tom Barkley in the office next door. And Tom, success has many fathers and only one mother. Tom is the mother of the Terra server. I mean, he carried the sucker full term. I mean, and to this day it continues to enhance it. And every once in a while I come in and help a little bit, but it's really Tom who's done everything. And if you think the word Terra server, think the word Tom Barkley.
What are you proudest of in your career?
Oh, gee, probably the people I've worked with and helped mentor. It's interesting. When you're younger, you think mostly of the things you did, and as you get older, you think more of your kids and how proud you are of your kids, or your, other people you've helped in their careers. But I think giving a straight answer to, what projects are most interesting. I was around at the birth of relational databases. That was a great thing. I mean, again, Ted Codd helped out a lot. He was, he wrote this paper about that relational databases would be good things. Don Chamberlain and Ray Boyce had this language called SQL that worked out pretty well. There are a few other,
So I heard.
there are a few other people who were, literally mothers of the success of relational systems. There were people at Berkeley, Mike Stonebreaker, Larry Rowe, Gene Wong, who worked on a project called Ingress that, was in a parallel universe to the IBM effort, and many of the innovations were synergistic between those two groups. So, so System R was a lot of fun, and it's every researcher's dream. You have a lot of fun, you do something innovative, and then people make billions of dollars off it. And that doesn't happen very much in a career. I worked at Tandem Computers, and we built yet another SQL system called Nonstop SQL, and that was a distributed, fault-tolerant, blah blah blah.
Did you work here in Cupertino, or?
I was in Cupertino in Tandem, and that was both a lot of fun.
I got a tour of their building when they were one building when I was in junior high.
Okay,
I lived a mile from Tandem.
Yeah. I mean, when I showed up there were like 100 people in the development division. It was a startup. It was, it was just an enormous amount of fun, and we were all, very high velocity, not a lot of process, and we accomplished a lot with very few people in a very short time. So that was fun. And since I've been at Microsoft, I feel like I'm an ex officio member of the SQL Server group, and I take some pride in the success that they've had. Again, you know, more or less I've been dating that group rather than actually being a member of the family, right? So I mean, they're doing all the work. Every once in a while, I get to come in and either, you know, listen or help, give some advice or just encouragement. But so SQL is, I mean, everybody who's involved with SQL Server ought to be really proud. It is a great product. And the Terra Server, I guess I've been much more directly involved with. And the thing I've been spending a lot of time on in the last, I don't know, 5 or 6 years, is I've been trying to get scientific data available on the internet to all scientists and to everybody. And so it's the information at your fingertips story for science data. Mm-hmm. And
can you give me some examples?
Absolutely. So the particular group I've been working with is the astronomers, and the probably
He's an astronomer.
Are you really?
Okay. Not really. I'm an amateur. I studied
All right.
planetary
So,
science.
well, hey.
He's
so,
understating it. He's always
Okay.
talking about. He always tells us whenever something is coming up.
But so the story is that the astronomers are a wonderful group of people to work with because they know a lot of astronomy, and they know a lot of chemistry, and they know a lot of physics, and they know a lot of mathematics, and they know a lot of Unix, and they know a little Windows, and they're just really bright, and they are not in it for the money. I mean, they're in it because they love astronomy and they're just very curious about things. And this particular group I've been working with mostly set out in 1988 to build a telescope that would survey the distant galaxies, the northern hemisphere of the universe. And this was before there was a very clear story about dark matter and dark energy. But they knew they were going to find something if they looked out there, because every time you look in a new way in a new place, you find something. So they built this telescope, and here it is. It's 1998, and they've got first light, and the data avalanche is about to show up on their doorstep. And they've been building the software to deal with this data since 1992, and it's not working. And Alex Saleh asked his good friend Charles Simonier, who works at Microsoft, whether Charles knew anybody in the database area who might be able to help him, and Charles said, well, you might go talk to Jim. He's not doing very much. He's in research, you know, he's goofing off. And
Is that really the truth?
he probably said something like that, you know, Charles. So Alex showed up,
Yeah.
and he said, you know, you've been working on the Terra server, you know, have you ever thought of looking the other way? I mean, you know, it's looking down, you look up, you know, it's a celestial sphere instead of the geoid. You know, it's the same problem. I said, oh, Alex, we're busy, go away. But we gave him a bunch of advice and some software, and he went away, and he started asking these really intelligent questions. Like I said, these astronomers are, and so you always look for people to work with who are, you know, smarter than you are. At least I do. And Alex is definitely in that category. So I said, hey, I want to work with this guy. So gradually I got suckered into helping more and more with the astronomy data. And the fundamental problem they have is that they have this data avalanche coming, and the pixels get turned into what's called a catalog. Okay, so and there's a million lines of code. It's a pipeline that says, galaxy, star, spiral galaxy, elliptical galaxy, and the axis of the ellipse is this, and the orientation of the ellipse is this, and the magnitude in this spectrum band is this, and and you get all these numbers. And so these pixels turn into like 400 numbers for a blob of pixels. And what are you going to do with it? And that's called the catalog entry for that object that you've recognized. And the catalog ends up having a couple billion entries in it. And so you're talking about terabytes of data. And what the astronomers are doing is they're either looking for haystacks or for needles in a haystack. They're looking for rare objects, quasi-stellar objects, QSOs, which who knows what the hell they are, but we think they're black holes in the center of galaxies. They are beacons to the distant universe. So these QSOs have something called a redshift, which is how much the light is redshifted when you look at it, which is a surrogate for how far away this thing is. High redshift means far away. Okay, so when we started, the highest redshift objects were 4.2. year one of the Sloan, they found 90% of the highest redshift quasars. We're now at 6.3 or 6.4 redshift. I mean, so found a lot of needles in the haystack. Okay, and the reason is the Sloan is just looking at the whole sky. and incidentally, how do you find the high redshift quasars? Select star from spec obj where z is greater than 5. That's all of the quasars with a redshift greater than 5. It's easy, okay? And pretty easy question to ask as well. So computers are great at finding needles in haystacks. Paradoxically, they're bad at finding haystacks. Haystacks are, how is the matter in the universe distributed? What's the distribution of matter? That's a global statistic about the whole database. People can look at a picture and see the haystack right away. Computer looks at a picture, you got to do a lot of programming to recognize a haystack. There's no select haystack from from spec obj thing. So the SQL guys have been working on business intelligence and data mining, and they're trying to put haystack algorithms into SQL. I mean, this is one of the grand challenges that we face. But so I think the challenge we have is that the astronomers, they had this data coming, and all the software they built, as bright as they are, wasn't working. And in particular, they knew that they had terabytes coming, and the software they had was 100 times too slow. So step one, I worked with them, and we tried to make their software run 100 times faster. And we gave up after about 6 months, and I said, just for the sheer hell of it, why don't we just take your data and put it into SQL and see how it goes? So we did that. They had concluded early on, they'd look up at the sky and they said, gee, I see objects. And they looked around at the database world and they said, object-oriented databases, that's what we need. So they went and invested in an object-oriented database. And it wasn't working. And the object-oriented database guy said, you got to use our stuff because relational just doesn't work for you. I mean, you got objects, we got objects. They have relations. You don't have relations. So we took their objects and we put them into SQL, and out of the box, it beat the performance requirement. And they built, I don't know, 500,000 to 1 million lines of code to process this data, and they got to throw that code away. That seemed like a good thing.
Yeah.
Not a pleasant thing, not an easy thing, but a good thing. So, and they had an ad hoc query interface, so they could ask questions and get back answers. And so we took this and we built a website. We said, gee, this is the world's best telescope, or one of them. We could use it to teach astronomy to kids. Give them the data, and let them rediscover Hubble's constant the way Hubble discovered it. Participatory science. And so the National Science Foundation, which is a sponsor of the Sloan, encourages people to take their science and make it accessible to the public, and especially to encourage science education.
And astronomy, I just point out, is very, very, very good about this.
Right.
Always.
Astronomy is very good and has some virtues. I mean, kids love dinosaurs. See? They also love astronomy. There are pictures, so you can teach mathematics through astronomy. It's really hard to teach mathematics straight out. Here's Euclid's, geometry. Well, if you can start out saying, well, this is the way planets go around the sun, and it's this thing called an ellipse. And, and there's an equation that actually describes an ellipse. Isn't that cool? Well, I mean, that actually is a much more a graphic way, and actually probably more useful, because it allows the kid to form a conceptual model of what an ellipse might be useful for, and what equations might be useful for, which is describing the motion of a celestial object. So you're right, astronomy is a really good vehicle for teaching science. It's also a good vehicle for teaching data analysis. I mean, here's a whole bunch of numbers. Now, it's hard to get kids excited about balance sheets. Okay?
Yeah.
It's a little easier to get kids interested in the fact that these stars have these magnitudes. Some of them are bright, some of them are not bright, and look, they sort of follow this curve. And and you can start teaching the black body radiation, and then you can show that the black body radiation isn't exact and that there are errors in measurement. Sometimes the errors are systematic. You know, so you can use this as a vehicle for teaching many aspects of science, and also of handling quantitative data, displaying quantitative data, graphing things. Okay, so we built a website for kids to get to the Sloan data. And, you know, the joke is that if it's easy enough for high school kids to use, it might be easy enough for professional astronomers to use too. So, in fact, we've had a situation where it's the easiest way to get to the Sloan data is through this interface, and many professional astronomers use it, as well as the outreach. And the collaboration, now they made the decision to store, the Sloan Digital Sky Survey made the decision to store their catalogs in SQL Server, and there's a kind of cooperative relationship between Microsoft and them. What happened next is that this is just one archive, and what many astronomers want to do is to compare the Japanese data with the European data with the American data. They want to compare the Hubble Space Telescope and radio telescopes with optical telescopes. And so there's this idea of the worldwide telescope where you take all of the astronomy data of the world and you integrate it into one great big database. And that's one of the most exciting things going on in the way people do astronomy. There's a lot of things exciting happening in astronomy because the instruments are getting so much better. But what I've been working, I have a very close collaboration with this guy Alex Saleh at Johns Hopkins, and what we've been working on is how do you build the worldwide telescope, and you know, bringing this back to Microsoft and computers. The answer is XML, web services, databases. You've got archives all over the place. You need to have common schema. Everybody has to agree that there are these things. Well, first let's agree that there's the metric system, and let's agree to keep time in, say, seconds. And then let's go on and say, well, you know, there are these things called stars, and stars have some attributes, and these things called galaxies, and galaxies have some attributes. And you start building up a schema. Some people would prefer to call it a controlled vocabulary. Schema is a database geek word, and controlled vocabulary probably means something to everybody. Okay, so controlled vocabulary, or if you're, you know, you really want to get fancy, ontology. If you really want to get current, semantic web. Okay, those are all, you know, synonyms for each other, at least in my mind. Although they're not, because when somebody says schema, I know they're a database geek, and when they say the semantic web, I know they're a web geek, and when they say controlled vocabulary, I know they're a librarian.
Yeah.
You know, I mean, all right. So we got to have that. So because computers are really dumb at some sense, and you have to have a common lingo or a common schema, so that you can move data from one place to another and compare it and get it to be in the same units. I mean, if some stuff's in feet and the other's in fathoms, you know, it's not going to work out real well. You know, you'd like to all be in meters, all be in seconds, all be in ergs per square centimeter or some measure of flux, right? So, so you do that, and then you say, okay, now we need to be able to ask questions of a database and get back answers. Okay, so how are we going to ask questions? Well, you come up with some sort of query language. SQL is a good start. Okay, and how are you going to represent the answers? Well, you've got to be able to represent data, and XML is a good start on that. And the interface stuff ends up being web services. So it's really stunning. People have been wanting to build the worldwide telescope for a long time. In the days of paper, they wanted the worldwide telescope. That's what libraries are about. In the 1990s, they set out to build a worldwide telescope, and they had things like X25, if you're old enough to remember. But, you know, that was the pre-TCP kind of communications, and they were programming in C. They were Fortran, and I mean, it was a much more difficult world. So with the advent of the internet, and the advent of web services, and the advent of XML, in about 6 weeks, we built a virtual telescope. We got data from Sloan, from 2 Mass. We had a node at Caltech. We had a node in Chicago. We had a node in Baltimore. These nodes were all talking to each other using, and when I say 6 weeks, 3 graduate students at Johns Hopkins University, with some consulting from me and some help from Alex Saleh, did this and entered it in some .NET rodeo and got second place. I'm really impressed with the guy who got first place, because, I mean, for me, this was something people have been trying to build for 30 years, and these kids just knocked it off in their spare time during against the deadline. Right, exactly. So I mean, the tools are.
Now, of course, you designed the database, correct?
Yeah, the database. Like I say, I mean, I help, but I mean, it's not like I'm not doing anything. But I mean, my job is mostly to make other people successful.
But I mean, the queries have to be optimized.
Well, yeah, the queries have to be optimized, and the wonderful thing is, the SQL guys have done a great job on query optimization. I mean, the Sky Server, this thing that we put up, it takes in random SQL. You can go there and type in a SQL query, and we run it. And if it runs in less than 90 seconds or produces less than 10,000 rows, we'll give you the answer. If it takes more than 90 seconds, it's your problem, not our problem.
Yeah.
Okay, and we actually just use the optimizer. So it's not really quite accurate. Let me just go down. I mean, this is a geek show, so maybe I'll go down a geek thing. So
Absolutely.
so let's imagine now that you have a whole bunch of telescope data from a whole bunch of telescopes.
Okay.
What do you want to do with it? Well, you typically want to compare 2 surveys. Well, what does it mean to compare 2 surveys? Well, the astronomers don't agree on much, but they agree that there's a celestial sphere. They don't agree what the coordinate system is, but there's a transformation from every coordinate system to every other coordinate system. So you can take an object in one spot, in one survey, and you can say, I'd like to know about the corresponding object in the other survey. Okay? And that's a spot in the sky in the other survey. First possibility, they don't cover that spot. Okay? If they cover that spot, their survey might be newer than yours, in which case you've got an area about this big around, and you know that there's an object inside this error ball. And they've got an object that's about this big around, because they've got a much better telescope. So they could have 10 objects where you have 1. Other possibility, their survey is 50 years old, and their error ball is like that. Okay? So we're doing a spatial join between these 2 things, which is to say we're comparing a certain spot in survey number 1 with a certain spot in survey number 2. That's why it's a spatial join, joining these 2 data sets in the spatial domain. Okay? We could be joining it in the color domain or something else, but we're joining it in the space domain. Okay? And this guy has an error bar, and this guy has an error bar. And so you can think of this object here as being a Gaussian, and this object here as being a Gaussian. And you take those 2 Gaussians and you intersect them. And the area under the joint probability of those 2 things is the chance that those are the same 2 objects. Okay, so if the guy has a big circle and you have a little circle and your circle and his circle overlap completely, very likely they're the same object. If they don't overlap at all, very likely they're not the same object. Okay, so that's why it's called a Bayesian spatial join. Okay, so how do you do a Bayesian spatial join?
Yeah.
Well, it's not easy. Okay, first thing you have to do is you have to quickly weed out. You got 1 object here, and you've got a billion objects here. Which of the billion are even candidates? So you have to do a spatial search and find everybody in the neighborhood. One of the things I did for the astronomers is to figure out a way to hook relational systems to their spatial access method, and we built a spatial index for it. And that's part of the secret sauce of why the Sky Server is so zippy and why you can mouse around and find things with it. So now we've, for every object here, we can find the corresponding object here. And now we do something called a chi-squared test, which is a little piece of statistics, which is, if you know what the word Bayesian means, you'll know what the word chi-squared means. And that gives us an estimate of whether these 2 objects are probably the same. And if they are, we say, okay, it's above a certain threshold, the joint probability is above a certain threshold, it's a match. if it's not a match. And so the people who built the system fished around on the internet and found an open source SQL parser. They took the SQL queries that people submitted, they teased the queries apart, they take the queries and send them to the various servers. The servers give them an estimate of how many records are going to come back. Back comes the cardinality estimates of the various servers. They take those and they sort the servers, who's got the smallest answer first, and they say to the smallest guy, send your answer to the next biggest guy, the next biggest guy. Okay? A typical guy in the chain gets a downstream answer of all of the people who've matched behind him. He takes that set and matches it with his and does this spatial join with his set. He takes that answer set and passes it to the next guy up the chain. So you can join like a dozen surveys together. When we started, we only had 3 surveys. We're now up to about 15. So you can do a spatial join across all 15 of them and get back for a certain part of the sky all the objects that match. It is amazing. And the thing that's really amazing is that I know how it works inside. And the way it works inside is it runs every query twice. It sends the query out to find out the cardinalities, it gets back, it comes up with a plan, and then it sends it out again. And some of these guys are in Cambridge, England, and some of them are in Caltech, and they're spread all over the planet. And it's going out twice. And it's all going out in XML, and it's going out through this web services stuff. And I grew up counting instructions and counting bytes, and here it is, we're using a Unicode, and we're sending around XML documents. And if you've ever looked at an XML document, it's not really compact.
No.
And we're not doing any compression on this stuff. I mean, this was 6 weeks, let's get it done kind of mindset. Just hack this thing together, and it works. And in fact, you say submit, and a second or two later, back comes the answer.
Yeah. It is amazing.
I mean, thank you, Moore. Thank you, Gilder. I mean, so the wires are fast, the processors are fast, the RAM is fast, the disks are fast, and if the answers are bigger, then it slows down. But it's amazing how simple it is, how simple the architecture is, and it's also amazing that these archives now are machines that are sitting in the closet with like 0 maintenance, and they're always up. Okay? I mean, it's quite a robust design, and I could imagine putting this together and having it work for the stunt, but not work a month later. And this thing's been up for many, many months, in fact, actually 3 years now, and works, and I could give you a demo now, it would probably work. I mean, occasionally something doesn't work, but it's because the power failed or the system. But it's really stunning how robust it has been. So you can tell I'm a believer in this
Absolutely.
web services stuff. I mean, it's just having done it before barehanded, this is so much easier.
Yeah.
And because it's a web service, I can write my own client.
Right.
For it, consume it, and
So-
program against these objects.
Right. So, I mean, one of the things we've done is put a web services interface on the Terra server. And Tom, when I say we did it, one of the things Tom Barkley did is put a web services interface on the Terra server. And the story behind that is also an interesting one. Microsoft is big on web services. And so the evangelists are out evangelizing web services.
Yep.
And they went to MIT and they said, you guys should be teaching web services. And Hal Abelson said, okay, I'll bite. I'll teach web services. How do I do that? And the guy says, so he says, well, you teach web. He says, well, what web services you got? We said, we got this great web service sum. You send us 2 numbers and we add it together and send you back the answer. He says, I'm going to have a hard time persuading my students that they need to use a web service to add 2 numbers together. I mean, we got an instruction in the machine to do that. So the guy went away and he says, we need to have something that people, don't have on their desktop. Okay, so we need to have web services that do something, and quote of the day is not it.
Yeah.
So you got to have something that has data associated with it. So what do we got? Well, they found Tom, and they said, Tom, can you put a web service on Terra server? And Tom said, sure. What's a web service? And they said, not to worry, we'll send somebody by. So they sent Jeff Richter over, who had been writing a .NET web services book, and Jeff and Tom cooked up the wrapper for the web services wrapper for, and this was in the very early days of, VS.NET, where, the tools were pretty primitive. But they did put it up, and it was a huge success because the students then could do applications that went off and got maps, and that gave, they had this visual aspect to their apps, and it was just and they found a few other web services out there that they could get addresses and address lookup, things like that. So it ended up being a big success.
Have the astronomers told you any stories about how they're seeing things in a new way within these systems?
Yeah, it's funny. As with everything, there are believers and there are non-believers. And I think we're still in the state that it's maybe 5 or 10% believers and 90% not believers. I mean, the astronomers are doing their job pretty much the way they did it last year and the year before. The typical style for astronomers is you FTP the data you need, and then you party on it locally, and they are not used to going to a data center and getting the data from a data center. In fact, many astronomers go off and collect their own data, and they have this notion of primary and secondary data, as do many other fields, and that real science is done on primary data that you gather yourself. And this is getting harder and harder and harder in the sciences because you're having instruments like the Large Hadron Collider that costs $10 billion, and it's hard to get personal time on the LHC, like impossible. And so you have teams of literally hundreds of people who are working at SLAC on the Barbar experiment or at the LHC, on Atlas or CMS. And these people, there's one group of people that gathers the data, and there are other groups of people who do data analysis on the data. So this different style of science, which doesn't replace the individual investigator, but gives the investigator access to science databases that they then analyze and mine. It's a different style of doing science, and it's mostly the younger generation of scientists who are taking that approach and who are fundamentally saying, in this new world, there is these different sources of information, and much of what we do is look at, compare and contrast these different sources, because many of the discoveries happen when you look at a new place or you look at old data in a new way. So an example of this, not from astronomy, but I think it's a good one, is the pentaquark. So some people in Japan found a new form of matter, which is 5 quarks glued together. And once they announced that they'd found this, the people at CERN and the people at SLAC and Fermilab and a few other places went and looked in their archives. And lo and behold, our same particle was hitting in their archives. So, so this is the needle in a haystack business. So, the physics community is right now looking for the Higgs particle, and the LHC is built to, find the Higgs particle. People down the street at the SLAC are looking for the Higgs particle like there's no tomorrow.
Where's the LHC?
That's in Geneva, and it's the Large Hadron Collider, and I think it's a 27-kilometer diameter ring, and and one of the things that's interesting is it's going to be producing data at a good rate, about a gigabyte a second, and so they need to move data at about a gigabyte a second to the United States, and they need to move it to Japan, and they need to move it to Brazil, and they need to move it, because each of these countries has put a fair amount of money into building the instrument, and the scientists in those countries want to have access to the data. So we've been working with them on moving data at high speed, and the goal is to move data at a gigabyte a second from CERN to Pasadena.
What is this thing doing to gather that kind of data? What?
Oh, well. Okay.
Well, that sounds like a fun project to get you involved in.
Well, what's it doing? So it's running particles around in a ring at very high speed and high energy, and then it's colliding them with matter, and in fact with each other, and watching what comes out. And what comes out They have detectors that are half the size of this building, and viewers won't appreciate what that means. So
It's big.
It's big. The detectors are huge. And the small one they're building on the surface, and the big one, the big detector is so big that they have to build it in place. So I've seen the small one, I haven't seen the big one. The small one is 4 stories high. Okay? It's, which is to say, about 100 feet high. Okay? Is that right? Yeah, I mean, that would be only, it's 10 stories high. It's about 100 feet high. And it's about a football field long. Okay? So that's the small one. The big one's bigger. Okay? So what that thing is full of is sensors. And the sensors are actually picking up several terabits of information per second. They throw away 99.99% of it and say, that was an electron, let's forget about that. That was a proton, we know about those. That was a boson, no problem, we know about those. Okay, here's a potential Higgs particle. Okay, let's save that one. What they're left with is a gigabyte a second. Okay, so they're throwing, what they're left with is the interesting stuff. And you have to appreciate that in this new world, we can build sensors that collect information like there's no tomorrow. I mean, we have cameras sprinkled all over the place. You know, and each camera is only generating a megabyte. Okay, but 1,000 cameras is a gigabyte. And, you know, I think Microsoft probably has 1,000 cameras running on campus. Okay, there's a gigabyte a second, if you wanted to save it. And why not? I mean, you can compress those things. I mean, we could go down that road and say, okay, but you get the picture that we're going into a world in which we can instrument everything.
Yeah.
And you just were talking to the My Life Bits guys.
Yeah.
You can capture everything. So what? Now what? What are you going to do with it? Okay, and I mean that's the challenge that we're facing. Is what are you going to do with it?